Come on, my dears, let us proceed further in chapter number 1. Let me revise 2 points. One is electromagnetic induction and second is Lenz's law. What was the definition of electromagnetic induction? Remembered? Whenever there is a change in magnetic flux associated with any circuit, then some EMF is generated or developed in that circuit which causes some current to flow in a closed path. This EMF is called induced EMF, this current is called induced current, and this very phenomenon is called electromagnetic induction. And then last time we had also studied Lenz's law. You know the statement of Lenz's law. Let me remind. Direction of induced EMF and induced current are always such that they can oppose the very cause producing it. Okay. Now, my dears, let me know who had invented about induced EMF, induced current and electromagnetic induction. You must have remembered it was none but Mr. Michael Faraday. Later on, the direction of induced EMF and direction of induced current was decided using Lenz's law. So, it was Mr. Lenz who had determined the direction of induced current. Okay. Now, question arises, of which magnitude we will get induced EMF. What will be the magnitude of induced EMF? Let us see. That result was devised by Mr. Faraday, and that result is known as Faraday's law on electromagnetic induction. What is that law? I am showing you. Let us see now Faraday's law on electromagnetic induction. Fine. Consider this as a time scale in which this instant of time is suppose small t. This instant of time I am taking t plus delta t. Fine. Now between these two instants, what is the time interval that has lapsed? It is this minus this, so it is delta t. Fine. At time t, the magnetic flux linked with a given closed circuit is suppose phi, and at time t plus delta t, suppose magnetic flux linked with that circuit is phi plus delta phi. Now what is the change in magnetic flux? This minus this, so it will be delta phi. Fine. Now tell me, in this much time there is a change in magnetic flux by amount delta phi. Now you know, whenever there is a change in magnetic flux, we are going to get induced EMF. Now if you measure that induced EMF in a time interval, we will call it average induced EMF, and that is shown by symbol average of capital E. And how much is this average induced EMF? That was derived by Mr. Faraday, and that result is this: average E equals to minus delta phi by delta t. Remember, this is delta phi by delta t means ratio of change of magnetic flux to the time lapse. But tell me, why we are putting here negative sign? Do you know that? Direction of this induced EMF obeys Lenz's law. So this negative sign indirectly shows the presence of Lenz's law. This EMF will always be getting induced in such a direction such that it can oppose the very cause producing it, and this is nothing but Lenz's law. That's why we say negative sign in Faraday's law indicates presence of Lenz's law. Fine. Now this is the average induced EMF which you are going to get in this much time interval. But now if we want instantaneous induced EMF exactly at time t, then what we should do? We should reduce this time interval delta t. We should make it gradually smaller and smaller. So mathematically we can write limit delta t tends to 0, delta phi by delta t. Remember, when in this ratio, when you take this time interval tending to 0, then we are going to get value of EMF exactly at time t, which is called instantaneous EMF. Let it be shown by symbol capital E. Fine. This negative sign as it is, but in the language of calculus, what is this? Limit delta t tends to 0, delta phi by delta t. What is it? It is d phi by dt. Fine. And now this very result E equals to minus d phi by dt itself is known as Faraday's law on electromagnetic induction. Let us now give statement of Faraday's law. This is the mathematical form. Statement you can give it this way. Value of induced EMF developed in any circuit is always equal to negative value of time rate of change of magnetic flux linked with that circuit. I repeat, value of induced EMF developed in any circuit is always equal to negative value of time rate of change of magnetic flux linked with that circuit. Fine. E equals to minus d phi by dt. Fine. Now let me write SI unit on both the sides. What is this induced EMF after all? It is nothing but some sort of potential difference. And you know SI unit of potential difference is none but volt. So instead of E, I am writing its unit. Come on, volt. You know SI unit of magnetic flux, it is Weber. SI unit of time is second. Okay. Transfer this. So Weber will be equal to, come on, volt into second. Weber equals to volt into second. Remembered? Last time I had given 3 units of magnetic flux which were equivalent. First was Weber, second was Tesla into meter square, and third one was this, volt into second. Volt into second. Okay, fine. Now my dear, here we have considered a coil having only one number of turn, only one turn. But not necessary that whenever you consider any coil, it should have only one turn, not necessary. It may have, say, n number of identical turns. If a given coil has n number of identical turns, and if time rate of change of magnetic flux linked with every turn is same, then naturally we will have induced EMF also n times. How? I am showing you. Come on, mathematically we can write E equals to minus d phi by dt. Yes, E equals to minus d phi by dt. But instead of small phi, I have written here capital phi, which is nothing but total magnetic flux linked with a coil having n number of turns. With one turn, if magnetic flux linked is small phi, then with n turns it will be multiplied by n. So now it is n into small phi. Capital phi, remember, it is equal to n into small phi, where n is total number of turns. But for a given coil, its total number of turns is constant. So I can definitely take it out of the symbol of derivative. Come on, minus sign as it is. N is taken out and left is now d phi by dt. d phi by dt. Now this is the general expression of Faraday's law on electromagnetic induction. And here n is total number of turns. If it is only 1, you may write n equal to 1. Then ultimately you will get E equals to minus d phi by dt, which we had seen earlier. Come on, E equals to minus d phi by dt. Simple. Now let us see different methods of obtaining induced EMF. Different methods of obtaining induced EMF. First, it is relative motion. Look, if you have a magnet and a coil, and if you produce relative motion between the two, then naturally during the relative motion what will happen? Either distance between magnet and the coil will decrease or the distance will increase. If distance is decreasing, then magnetic flux will increase, and if distance is increasing, then magnetic flux will decrease. Then you know, whenever there is a change in magnetic flux, you will get induced EMF. Fine. Second is by way of rotation. Suppose you have stationary magnetic field, correct? And in that you have some coil, and if you rotate that coil, then when you rotate at that time, you know the formula of magnetic flux, phi equals to AB cos theta. But what was that theta? Angle between vector A and vector B. When you rotate the coil constantly, that angle is keeping on changing. Phi equals to AB cos theta. When theta is changing, naturally phi will change. And because of the change in magnetic flux, you will get induced EMF. Come on, third method is this, by change of magnetic field. Suppose you have a source of magnetic field such that it keeps on changing with time, then naturally through a given coil, if magnetic flux is passing, then you know its formula, phi equals to AB cos theta. But in that capital B is magnetic field. If it is keeping on changing, naturally magnetic flux will change, and because of that also you will get some induced EMF. Fine. Let us see now fourth method, that is non-uniform magnetic field. Here also magnetic field is keeping on changing, but here magnetic field is changing with time, and here magnetic field is changing with position. If you have certain region in which magnetic field changes depending upon different position, and in that if you are just moving any coil, then as that coil passes through different positions, naturally because of change in magnetic field strength, phi equals to AB cos theta, when B is changing, phi also will change, and because of change in magnetic flux you will get some induced EMF. And the last method is this: if the coil is flexible, if the coil placed in a magnetic field is flexible such that its dimensions, its size can be changed, then thereby you can change the magnetic flux, and because of change in magnetic flux, naturally you will get some induced EMF. So these are the various 5 methods whereby you can have induced EMF. Now, what is called motional EMF? Any EMF which is obtained by motion and by change of magnetic flux is known as motional EMF. EMF obtained by changing magnetic flux during the motion is called motional EMF. Now here in our syllabus we have to study one simple method whereby we can get motional EMF. I am showing you how. Come on. In this figure you will find cross symbols. Small cross symbols I have put here in the figure. You know, each of these cross symbol indicates one magnetic field line which is entering plane of the figure perpendicularly. So it is perpendicularly inward. Had it been perpendicularly outward, we could have shown it by symbol of dot. So please remember, it is the pictorial notation for showing the magnetic field lines, whether they are going inside the plane of the figure or they are coming outside the plane of the figure. If they are going inside the plane of the figure, then we show it by symbol of cross. If it is coming outside the plane of the figure perpendicularly, we show it by symbol of dot. Right now perpendicularly inside, that's why everywhere I have put the symbol of cross. Fine. Now in this uniform magnetic field, you just consider a metallic frame having shape of English alphabetic letter capital U. This is capital U shaped metallic frame. Fine. Now these two are the parallel sides. Okay. Now between these two parallel sides, the perpendicular distance is L. Fine. Now what we have placed here? One conducting rod. Correct? Some conducting rod or conducting wire, and that conducting wire is placed over these two arms which are parallel, and perpendicular to those two arms is this conducting rod, and that conducting rod is now given motion towards the right hand side, say with constant velocity v. Fine. During the motion at time t, this rod is coming here at position PQ. Come on. At that time, the distance of this rod from this left end of the frame is suppose x. And now tell me, here you find one closed loop. What is a closed loop? This one, correct? And the area of this closed loop is suppose capital A. You know, for a rectangle, what is the area formula? Very simple. Length into breadth. This much is length. This much is length. And this much is breadth, which is x. Come on, length is L, breadth is x. Length into breadth will give you area of this loop. Fine. And now tell me, through this area, don't you find certain magnetic field lines are passing through this area? And you know, number of magnetic field lines passing through a given area is going to give you indirectly measure of magnetic flux. And what was the formula for magnetic flux? Phi equals to AB cos theta. Come on. Phi equals to AB cos theta. Remember what was theta? It was angle between vector A and vector B. Wait. This is the plane of the frame, and if you draw area vector, you know how to draw it? Perpendicular to this plane. Perpendicular to this plane, I can draw area vector this way. Correct? This way. Perpendicular to it. Okay? So this perpendicular vector is area vector which is going inside. And magnetic field vector is also going inside. I mean to say vector A and vector B, right now they are pointing in the same direction. Angle between two vectors in the same direction is 0 degree. Come on, cos 0 is 1. And value of A is how much? L into X. Value of A is how much? L into X into B into cos 0 degree, which is 1. And now tell me, phi equals to BLX. Phi equals to BLX. Tell me in this formula, B is constant, L is also constant. But as time passes on, this conducting rod is moving towards the right hand side. So naturally, X will keep on increasing. When X is increasing, naturally, magnetic flux will increase. You don't have to bother whether magnetic flux is increasing or decreasing. You simply have to notice the change in magnetic flux. If here magnetic flux is changing, naturally we have some induced EMF which is here developed across the two ends of this rod. Now my dears, try to take a special interest to understand this phenomenon. How EMF is generated here between these two ends, I am showing you. Look, this is a metallic rod, correct? It contains plenty of free electrons, okay? And each electron, you know, it is a negatively charged particle. And for a negatively charged particle, what was the formula for magnetic force exerted on a negatively charged particle? You have studied in third semester. Remember, that formula was this: vector Fm equals to E into formula of magnetic force exerted on electron. You have studied in third semester. It was this formula. Vector Fm equals to E into vector B cross vector V. Remember? Actually, original formula was vector Fm equals to Q into bracket vector V cross vector B. Correct? Come on, Q into vector V cross vector B. But at that time Q was positive charge. Q was positive charge. It was a magnitude of a positive charge. But here we are talking about electron. Electron has negative charge. So you should write Q equals to minus E. Q equals to minus E. Out of minus E, I have kept E outside and minus sign I have taken inside. What was inside? Originally vector V cross vector B, and if you associate negative sign with that cross product, then the order will be reversed, and now it is vector B cross vector B. Okay, fine. So direction of magnetic force exerted on electron is in the direction of vector B cross vector V. In the direction of vector B cross vector V. Wait. If you want this direction, you should find out this direction. What is this direction? Vector B cross vector V. I am showing you. Mind well, when this rod is moving towards the right hand side this way, correct? Each electron inside gets the same velocity as that of rod. Each electron obtains velocity equal to velocity of rod. Velocity of rod is right now towards the right hand side. Then each electron has also velocity towards right hand side. Fine. And where is magnetic field? Magnetic field is perpendicularly inside. Perpendicularly inside. So now this is the situation. Look. If this is velocity and this is magnetic field, situation is like this. Correct? This is magnetic field, this is velocity, correct? These two vectors are mutually perpendicular, this way. This is vector B, this is vector V. Right now the situation is like this. And now I want vector B cross vector V. Tell me, if this is vector B, this is vector V, then first of all, what should I do? I should think of a plane passing through vector B and vector V. That plane is this plane, horizontal plane, correct? And now, for this horizontal plane, what is the right-handed screw which is perpendicular to it? Perpendicular to it is this screw, correct? This way. Fine. Now this screw I should rotate in a manner. Right now the situation is like this. Vector B is inside. Let it be this vector. Vector V is toward the right hand side. Let it be this vector. Okay? This is vector B, this is vector V. And now I want vector B cross vector V. Okay? Think of a plane passing through these two vectors. That plane is this. And now I should imagine a right-handed screw which is perpendicular to this plane, this way. And now I am supposed to rotate this screw in a manner, first vector rotates towards second vector. In this product, tell me what is the first vector? Vector B. Second vector is vector V. This is vector B, this is vector V. I should rotate vector B towards vector V through the angle between them, this way, right? And now tell me, if this is the right-handed screw, here is the head of that screw, and here if I just put the screwdriver and if I rotate it this way, correct? Then it will advance vertically downwards, correct? And you know, direction of advancement of right-handed screw gives us direction of a vector product. So right now, this vector product has direction vertically downwards. That is why we say direction of magnetic force is also right now vertically downwards. So on this electron, if the force is vertically downwards, look here, force is vertically downwards. Naturally, it will be compelled to move downwards. So now each electron gets displaced vertically downwards in the rod this way. And tell me, in this process what will happen? This end, because it loses electrons, it would become positive. And this end, because it gains extra number of electrons, it will become negative. This end achieves positive potential, which is higher potential. This end achieves negative potential, which is lower potential. So ultimately, you will have some electric potential difference across these two ends of the rod. And same potential difference itself is known as induced EMF. Let it be capital E. And if it is capital E, come on, according to Faraday's law, E equals to minus d phi by dt. E equals to minus d phi by dt. Come on, E equals to minus d phi by dt. Minus d by dt as it is. What about formula phi? Formula phi is, come on, BLX. Formula phi is, come on, BLX. And tell me, B is constant, L is constant, so I can take them out. Minus B into L and then into dx by dt. Come on, dx by dt. Tell me what is this dx by dt? From first semester, time rate of change of position of a body. Time rate of change of position of a body would give you instantaneous velocity, and here velocity of rod is constant equal to v. So this dx by dt can be replaced by velocity of rod, which is v. So here when you write v, now it will be read like this, minus bvl, minus bvl. Here it is, minus bvl, correct? Let me write unit of each term on right hand side. Unit of magnetic field, come on, Weber upon meter square. What about unit of velocity? Meter per second. And what about unit of length? Meter. And now meter into meter, meter square will be getting cancelled with this meter square. So left is Weber upon second. Here it is, Weber upon second. And what is Weber upon second? What is Weber upon second? It is nothing but volt. So instead of Weber upon second, I can write volt. Instead of Weber upon second, I can write volt. Simple. What do you mean by Lenz's force? Look. Here we have a conducting rod which is moving in a magnetic field. At that time, we have some induced EMF developed across its two ends. And in this situation, this end has become positive. This end has become negative. So mind well, this moving rod behaves as if it is a battery of this much EMF. It behaves like a battery of this much EMF. And you know, if you have got source of electric current, which is nothing but EMF, this is what you have it here. Now this rod behaves like a battery, so it will send current in the outer circuit. This is the outer circuit, correct? And you know direction of current in the outer circuit, which is the direction from positive to negative. From positive to negative. Look here this way, from positive to negative, correct? Inside the battery, it will be from negative to positive. It will be from negative to positive, this way. But outside the battery, come on, from positive to negative. So this is how you will have induced current passing through this rod. Now we find that whenever there is a current carrying wire in a magnetic field, and if it is set in motion, then we find some force is exerted on the rod in a direction opposite to its motion. Such a force which is exerted on the rod or wire moving in a magnetic field carrying some current, which is always produced in a direction opposite to motion, is known as Lenz's force. Why it is called Lenz's force? Because the root cause for the production of such a force lies in Lenz's law. That's why we call it Lenz's force. If you want to have direction of that force, if you want to have magnitude of that force, then you are supposed to use Amperes law. Remember Amperes law you had studied in third semester? It was like this. Vector F equals to I into vector L cross vector B. Tell me, what is the direction of vector F? It is the direction of vector L cross vector B. Tell me, what is the direction of vector L? Always in the direction of current. Through this rod, current is passing this way. Look here, this way. Through the rod, current is passing this way. That is upwards. Okay? And magnetic field is inside. So now situation is like this. This is vector L. This is vector B. Vector L, vector B. Vector L, vector B. Now think of a plane passing through these two vectors. Correct? This way. And now think of a right-handed screw perpendicular to this plane. That right-handed screw is this. And now just rotate this screw in a manner. First vector rotates towards second vector. First vector is vector L. Second is vector B. I should rotate this vector towards this vector this way. And in the same manner, I should rotate this right-handed screw. When I rotate it this way, correct? Come on, the screw will advance this way. That is towards left side, towards left side. Come on. That's why this force I have shown towards left side. Such a force which is exerted in a direction opposite to motion, it is resistive force. It is called Lenz's force because the root cause for the production of this force lies in Lenz's law. That is why this force is called Lenz's force. Okay, fine. A resistive force exerted on a moving and current carrying wire moving in a magnetic field is called Lenz's force. A resistive force exerted on a current carrying wire moving in a magnetic field is called Lenz's force. I repeat, a resistive force exerted on a current carrying wire moving in a magnetic field is called Lenz's force. Fine. Now tell me, if I want magnitude of this force, come on, magnitude of this is F. I as it is, you know vector A cross vector B, its magnitude is AB sin theta. Similarly, magnitude of vector L cross vector B, what is it? LB sin theta. What is theta? Angle between vector L and vector B. Come on, vector L is always taken in the direction of current right now, say upwards, this way, and vector B is right now inward. Come on, this is vector L, this is vector B. What is this angle? This angle is 90 degree. Fine. Come on, theta is right now 90 degree. Sin 90 is 1. So F equals to ILB. Come on, F equals to ILB. Fine. Now tell me, though this force is exerted towards left side, if I want motion of this rod continuously towards right hand side, and not only that, with the constant velocity, then what I need to exert? I need to exert an equal but opposite force on this rod. Opposite to this means this way. then I should provide a force of magnitude equal to F only, but towards right hand side this way. Come on. During the motion, if both the forces are exerted on the rod equal in magnitude, opposite in direction, then resultant force will be 0. Whenever resultant force is 0, acceleration will be 0. When acceleration is 0, velocity will be constant. So in order to have motion of this rod towards right hand side with constant velocity, you need to exert force on this rod towards right hand side. Come on. I am exerting force towards right hand side equal to F, and velocity is also in the same direction. Then what is the power which I need to spend for that? Come on, mechanical power. You have studied formula for mechanical power. What was that? P equals to vector F dot vector V. Vector F dot vector V. What is the expansion? Fv cos theta. Everybody, Fv cos theta. Here it is. Fv cos theta. Theta is right now 0 degree because external force is towards right hand side. Velocity is also towards right hand side. Angle is 0 degree. Fv cos 0 degree. Cos 0 degree is 1. That's why I written here F into V. Simple. What is F? F equals to ILB. F equals to ILB into V. And now what is current? Say magnitude wise, it is magnitude of induced EMF divided by ohmic resistance. Current equals to EMF upon resistance. Fine. L into B into V as it is. L into B into V as it is. Fine. What about magnitude of E? Magnitude of E, come on. For this motional EMF, what is the magnitude? Magnitude when you take here, minus will become plus. So it is BVL. Come on, this is the magnitude of induced EMF. Right now it is BVL. That's what I have written here. E equals to BVL. Into L into B into V as it is. LBV as it is upon R. And now tell me, B into B, B square. V into V, V square. L into L, that is L square upon R. B square, V square, L square upon R. Let it be equation number 1. And now tell me, will you get some electrical power also? Yes. When we are spending mechanical power, we are likely to get electrical power here. How? I am showing you. Here we are getting some induced EMF. And because of production of induced EMF, we also get some current. Then don't you know formula of electrical power? It is EMF multiplied by current. EMF multiplied by current is called electrical power. Fine. Now electrical power generated is given by this formula, EMF multiplied by current. Come on, E as it is. What about formula of I? Formula of I is, come on everybody, I equals to E upon R. Come on, I equals to E upon R. And tell me, E into E, that is square upon R. Square upon R. But what about magnitude of induced EMF here? When you take magnitude here, minus will become plus, so it is BVL. So E equals to BVL and it's a square upon R. Now tell me, when you take square here, it is B square, V square, L square upon R. B square, V square, L square upon R. Come on, give it equation number 2. Compare equations 1 and 2. Right hand sides are same. Right hand sides are same. So left hand sides also must be same. That's why I have written here PM equals to PE. Come on, PM equals to PE. Mechanical power spent is equal to electrical power generated. But mind well, here we have made one assumption. What is that assumption? Actually what happens when current is passing through this wire, it is going to dissipate some energy in the form of heat energy. You know Joule's law. You know Joule's effect. Then whenever current is passing through any conducting wire, some amount of heat is generated and ultimately that energy is getting dissipated outside from that wire. Okay? So actually there is a loss of energy here, but under ideal conditions, if we assume there is no loss of energy, there is no dissipation of heat energy, then we can say whatever mechanical power we are spending, same electrical power will be generated. So under ideal conditions, you can write PM equals to PE. Fine. Let us talk about now induced charge. Look, charge formula, everybody knows, charge is current into time. Charge is current into time. So delta Q equals to, come on, I into delta T. Come on, delta Q as it is. What about magnitude of induced current? It is magnitude of induced EMF divided by resistance into delta T. I equals to magnitude of E upon R. And tell me what is magnitude of E from here? From here if you take magnitude, then what is that? Come on, when you take magnitude, come on, it is delta phi by delta T. Delta phi by delta T. Come on, magnitude of E is delta phi by delta T into delta T upon R as it is. Delta T upon R as it is. Now delta T getting cancelled. What is left? Delta Q equals to delta phi upon R. Delta Q equals to delta phi upon R. What is the delta Q? Don't say charge, say induced charge. Say induced charge. And what is the delta phi? Magnetic flux. This is the resistance of the circuit through which induced current is passing. Okay, fine. Have you noticed one thing? Induced EMF depends on time. Induced current also depends on time. But here delta T getting cancelled. So we can say induced charge does not depend on time. Remember, induced charge does not depend on time. Okay. Now my dears, let us begin with numericals. Normally I have observed that students have some psychological grudge for numericals. Actually, let me tell you, numericals are the best source of fetching maximum marks, because there you need to understand the statement, you need to recall the proper formula, you need to simplify, you are going to get the answer, and nearly 3 to 4 marks depending upon the type of example, you will be getting encashment of the marks so very easily, correct? Otherwise, suppose in a subjective paper, if you have to fetch say 4 marks, and if this 4 marks is a total of 2 short questions, then 2 plus 2, then for writing a short question, answer of it, you will need to fill up nearly 1.5 page, and such 2 questions are there. So nearly after filling 3 pages, you are going to get 3 or 4 marks. And here within some 2-3 steps you may get the answer, and you will get very good marks if you just have the confidence and interest in the numericals. So I just appeal to everybody to pay very special attention for the numericals. Okay, I will take you in all the subjective details for the numericals, and you will notice now onwards. Okay, please read the statement, and whenever I say that just read the statement, not for the sake of reading the statement you should read, you should try to understand the statement, and for that you must read it minimum 2 to 3 times. If any numerical is there, suppose it is very easy, but you are not reading the statement perfectly, then you cannot solve it. And on other side, if the sum may be very difficult, but because you are reading the statement often and often, you are trying to understand it thoroughly, then you are likely to get the answer. So please form good habit and perfect habit. Perfect habit is that with total concentration, you should read the statement and nearly 3 times, please. So whenever I allow time for that, you don't do anything else, don't just take any gossiping, and you just concentrate in the statement. Okay. Now start reading this statement of first illustration in chapter number 1. Come on, read the statement. Look. In the very first numerical, they have, in the textbook, they have utilized one fact which they have not proved. Okay? That proof belongs to mathematics. So let me prove that result first, and then we will use it. Now what is that result? I am showing you. We find that average value of periodic function like sine or cosine over one periodic time is found to be 0. I repeat, average value of periodic functions like sine or cosine over one periodic time is 0. How to prove? Let us prove it in 2 different manners. First using mathematical formula, and then second using graph. I am showing you. First of all, try to understand what is the basic definition of finding average value of a given function over given time interval. I am showing you. Suppose given function of time is f as a function of t. Okay, we require its average value. Suppose over time interval small t. Then what you are supposed to do in a time interval from 0 to small t, at each instant you are supposed to find out instantaneous values of given function, and then you are supposed to find out their addition. That total you can find out by taking integration. Integration f as a function of t dt over this much time interval from 0 to t, and then that summation is to be divided by the same time interval, that is you must divide this by t now. Now tell me, integration f as a function of t dt from 0 to small t divided by small t, this will give you average value of given function in this much time interval. But right now, what is a given function? Given function, suppose I am taking sine function, then instead of f, I just put sine. Okay, come on. It is also a function of time right now. I am taking the function sine of omega t, where omega is called angular frequency. Fine. And now its average value we require, no problem. Just instead of as a function of t, you just write sine of omega t. That's all. And because we are interested in finding out this average value over one periodic time, then I just write the limits this way, 0 to capital T, 0 to capital T. And then that summation should be divided by same capital T. Fine. Suppose you require average value over half of the period, then 0 to t by 2, 0 to t by 2. Then here you may write 0 to t by 2, but if you are taking integration from 0 to t by 2, then here you should divide by t by 2. Because right now we require average value over one periodic time, then I am just specifying the limits this way, 0 to capital T, and then that summation I am dividing by capital T. Fine. And now 1 upon capital T we can separate, correct? Then come on, remember derivative of cosine function is minus sine function. Derivative of cos is minus sine, then speak reverse. Integration of sine is minus cos. Integration of sine is minus cos. Integration of sine of omega t is minus cos of omega t. And now you are supposed to take derivative of this part, and whatever answer you may get from, you have to divide this value by that answer. If I take derivative of this term with respect to t, then I will get the answer omega. Because omega is constant, d by dt of t is 1, omega into 1, that is omega, and by that omega I should divide this summation now. Come on, this value is this, and now divided by omega. And now what are the limits? Limits are 0 to capital T, 0 to capital T. I repeat, 1 upon capital T as it is. Okay, then integration of sine is minus cos, and then we have to take derivative of this part, which comes out to be omega, and by that omega we have to divide. We have to divide this value by omega, and limits are 0 to capital T, 0 to capital T. Fine. Now tell me, minus 1 upon t into omega, minus 1 upon t into omega, here it is, minus 1 upon t into omega, and then cos of omega t from 0 to capital T, cos of omega t from 0 to capital T. Come on, minus 1 upon t omega, this part as it is, cosine as it is, omega. What is the formula for omega? Remember, omega equals to 2 pi by capital T, where capital T is called periodic time, omega is angular frequency. Fine. Omega is 2 pi by capital T. Now instead of small t, I am supposed to put the upper limit first. Upper limit is capital T. After putting minus sign, in the same function, instead of small t, I am supposed to write 0. So cosine as it is, omega formula is 2 pi by capital T. Instead of small t, I should write 0. And now tell me here, t will cancel, correct? And cos 2 pi is 1. Here 0 into this will be 0. Cos 0 is 1. So it is 1 minus 1. 1 minus 1, 0. 0 into this part will be 0. So average value of sine function over one periodic time is 0. Similarly, average value of cosine function over one periodic time is also 0. Come on, can you prove that now? Using this, can you prove? Very easy. Look, instead of sine, What you should write? Instead of sine, you should write cos. That's all. Now remember, derivative of sine is cos. Then integration of cos will be only sine. So here you should write sine with plus sine, sine of omega t, and d by dt of omega t is omega. So you should divide by omega. I repeat, instead of sine you will write cos. Okay? Derivative of sine is cos. Then integration of cos is sine. Then you can write here sine of omega t upon omega. Then I mean to say, instead of cos you will get here sine. Here also you will get sine. Come on, tt will cancel. Sine of 2 pi is 0. So here you get 0, and 0 into this will be 0. Sine 0 is 0. So here instead of 1 minus 1 you will get 0 minus 0. 0 minus 0 is also 0. 0 into this will be 0. So average value of cosine function over one periodic time is also 0. Let us see this proof now using graph. Very simple. Graph of cosine is like this. Correct? And here this time is 0. This time is capital T. This is the time which is t by 2. Between 0 and t by 2, what is it? T by 4. Between t by 2 and t, what is it? 3t by 4. Now tell me, don't you find these values are positive? On the upper side, values are positive. On the lower side, common values are negative. Suppose summation of all these values is 25. Just imagine. Then here also it is 25. 25 plus 25, that is 50. But these all values are negative. And their summation comes out to be minus 50. Now tell me, summation of these two values, come on, 25 plus 25, that is 50. And if this is minus 50, then 50 minus 50 will be 0. So over one periodic time, the summation would be 0. When the summation is 0, when you divide by capital D, again it will be 0. Okay? Come on, for sine function, graph is this. And in this graph, you can say this time is 0, this is capital D, this is t by 2, this is 3t by 4, and this one is, come on, 3t by 4. From 0 to t by 2, how are the values? They are all positive. From t by 2 to t, how are the values? Values are negative. Suppose these values, summation of these positive values, suppose it is 40, then this will come out to be minus 40. And when you take summation of these two values, 40 plus minus 40, it will be also 0. So I mean to say, average value of sine function over one periodic time is also 0. Now please remember, my dears, nobody will take this pain to explain you in this much detail. Actually, I can straightway tell you that you remember this, okay? But just for your mental satisfaction and knowledge, I have explained this thing. But please now remember, in any case, you must remember, because this application, this result will be utilized many times. Average value of sine or cosine over one periodic time is 0. Please remember now. We are going to use it in the first numerical. Look, they have given magnetic field by this formula 0.2 sine of 50 pi t, this many Tesla. Now this multiplier of this sine function gives you maximum value of magnetic field. Let it be shown by symbol B0. Suppose this sine as it is. Now inside the sine function you can expect angle. In that angle the coefficient of time is always going to give you angular frequency, and that angular frequency right now I am showing by symbol omega t as it is. Fine. Now just compare given equation with the standard format. B equals to B0 sine of omega t. Fine. Now compare these two. When you compare, B0 will be, come on, 0.2 Tesla. What about coefficient of time? Here omega, and here it is 50 pi. So omega will be 50 pi. When you compare, come on, omega will be 50 pi. What about omega formula? Just now I told 2 pi upon capital D means angle upon time. Unit of angle is radian, unit of time is second. Fine. Now tell me, what is the formula for induced EMF? For induced EMF, you know Faraday's law, E equals to minus d phi by dt. E equals to minus d phi by dt. Come on, minus d by dt as it is. Instead of phi, what you will write? A into B. As such, we are supposed to write phi equals to AB cos theta. But whenever any planar loop is perpendicular to uniform magnetic field, at that time theta is 0, because theta is the angle between vector A and vector B. And when theta is 0, come on, phi equals to AB cos 0 degree. Cos 0 degree is 1. So remember, phi equals to AB. Whenever planar loop is perpendicular to magnetic field, please use this short formula, phi equals to AB. Now minus d by dt as it is, A as it is. What about formula of B right now? It is, come on, B equals to B0 sine of omega t. B equals to B0 sine of omega t. But because A into B0, this part is constant, I can take it out. And now derivative of sine, remember it is cos. That's why I written here cos of omega t. And now again you have to go for taking derivative of this inside part, which is omega. Why? Because omega is constant, d by dt of t is 1. Now minus a b0 omega, minus a b0 omega, minus a b0 omega cos of omega t. What about induced current? Very small formula. According to Ohm's law, current is EMF upon resistance. Induced current is magnitude of induced EMF upon resistance. Right now we are not taking magnitude, we are taking only EMF. Come on, induced current is induced EMF upon resistance. Come on, induced EMF right now it is minus a b0 omega cos of omega t. Minus a b0 omega cos of omega t upon R. Can you just write separately this much part? Minus a b0 upon R. I am taking separately. Minus a b0 omega upon R. Minus a b0 omega upon R, because this part is constant. I just separate it and into cos of omega t. Fine. Now this part is constant also, and that same part indicates maximum value of induced current. Let it be shown by symbol I0. So this part I just replace it by I0 into cos of omega t. Where I0 you must mention it is replaced for minus a b0 omega upon R. This part is replaced by I0. Fine. And now tell me, you don't know formula of omega? What is omega formula? 2 pi by capital D. Find out capital D, from that you will get 2 pi upon omega. This 2 pi as it is. What about omega? Omega is 50 pi. Omega is 50 pi. Pi will cancel. 2 upon 50. 2 upon 50, if you find out, it is coming out to be 0.04 second. Whenever, if it is possible to make the denominator 10, 100, 1000, you must make it just to simplify the value very easily. Here it is 2 upon 50. If I multiply numerator and denominator by 2, then it will be 4 upon 100. 4 upon 100 is nothing but 0.04. That many second. But given time, which is given to you in the statement, is 40 millisecond. 40 millisecond. What is milli? This submultiple milli means 10 raised to minus 3. Have you remembered the complete table of all the submultiples? 10 raised to minus 1, 10 raised to minus 2, 10 raised to minus 3, then 10 raised to minus 6, 10 raised to minus 9, 10 raised to minus 12, 10 raised to minus 15, 10 raised to minus 18, 10 raised to minus 21, 10 raised to minus 24. Respectively, all these submultiples are known as, in words, remember, deci, centi, milli, micro, nano, pico, femto, etto, zepto, yocto. I repeat, deci, centi, milli, micro, nano, pico, femto, etto, zepto, yocto. In that, milli means what? 10 raised to minus 3. Okay, fine. Now, 14 to 10 raised to minus 3, it is also 0.04 second. I mean to say, these two right hand sides are same, so left hand sides also must be same. So given time is just equal to periodic time. So in this example, you are given this time equal to periodic time, and now we are asked to find out induced charge. How to find? I am showing you. Can you see one thing here? As time will change, come on, current will change. I mean to say this current is not constant. If current is constant, you may use the formula I equals to Q upon T. But whenever current is not constant, you should use this formula I equals to, here right now current is not constant, then use this formula I equals to dq upon dt. I repeat, if current is constant, use the formula I equals to q upon t. But if current is not constant, use the formula I equals to dq upon dt. Look here, I equals to dq upon dt. Fine. Take this dt up, then you get dq. dq will be how much? I into dt. I into dt. Then take integration on both the sides. Integration dq and here integration I dt. Summation of partial amounts of charge will give you total charge. Fine. Let it be shown by symbol capital Q. Integration as it is, come on, formula of I. Right now it is I equals to I0 cos of omega t. I equals to I0 cos of omega t. And I just forgot to write here dt. This dt I have written, fine. And now, integration 0 to small t. Integration 0 to small t. Instead of small t, I should write here capital T. I should write here capital T because small t equals to capital T. Small t equals to capital T. Small t equals to capital T. Now I0 cos of omega t as it is. Again, I forgot to write dt here. Now tell me, I0 is constant, should be taken out. I0 is constant, should be taken out. Integration 0 to capital T, cos of omega t dt. Fine. Now I0 as it is. What about this part? Integration cos of omega t dt from 0 to capital T. 0 to capital T means what? Over one periodic time. Over one periodic time, the summation of instantaneous values of cosine function is 0. So this summation comes out to be 0. 0 into I0 will be 0. 0 into I0 will be 0. So induced charge you will get Q equals to 0. Correct? Induced charge is right now 0. Next. Read the statement of sum number 2. Induced EMF according to Faraday's law minus d phi by dt minus d by dt as it is, phi equals to AB. Just now I told you, whenever planar loop is perpendicular to uniform magnetic field, you should use the formula of magnetic flux, phi equals to AB. Phi equals to AB. Come on, minus d by dt as it is. What about area? Given loop is circular, and for a circle, what is the area? A equals to pi r square. Pi into radius square into B as it is. Come on, minus as it is, pi into B is constant taken out, d by dt of r square minus pi into B. What is the inside part? Inside part is a function of r, and you want to take derivative with respect to time. Can you take it directly? No. Apply chain rule. You must take derivative of this part first of all with respect to r, and then separately you should take derivative of r with respect to t. Fine. D by dr of r square into dr by dt minus pi into b as it is. D by dr of r square, you know by formula it is 2 into r. How? D by dr of r is to n, then it is n into r is to n minus 1. Just put n equal to 2, then you get 2 into r is to 2 minus 1, that is 2 into r. 2 into r. This dr by dt as it is. And now tell me minus, value of pi is 3.14. Come on, value of b, they have given 0.04 Tesla. It's 2 as it is. But what about radius of circular ring or loop? They have given 2 centimeter. Convert it into meter, multiply 10 raised to minus 2. And this is dr by dt means what? Time rate of change of radius. But if that radius is increasing with time, then time rate of change of radius is positive. But here radius is decreasing with time, so time rate of change of radius will be negative. So this dr by dt right now it is negative, and the rate which they have given is 2 millimeter per second. Per second is okay, but this radius you can't take in millimeter. SI unit of radius is meter. I must convert it into meter. Millimeter to meter, multiply 10 raised to minus 3. Now simplify. Minus minus will become plus. Answer is exactly 10.048 into 10 raised to minus 6, this many volt. But don't you know, 10 raised to minus 6 volt is 1 microvolt. See, in the examination, if you just leave this as a final answer, no problem. But if by chance they ask the EMF in microvolt, then you know 10 raised to minus 6 volt is 1 microvolt. So 10.048, this many microvolt. In textbook, you know what have they done? They have expressed this answer in terms of pi. According to me, you should not do that, because in physics, for angular displacement, for angular velocity and for angular acceleration, you may express final answer in terms of pi for all rotational variables, but not for other physical quantities. This is not a rotational variable, so we must put the value of pi and we must find out the exact answer in decimal point. No problem. You should not leave pi as it is, you must put the value. But suppose in the examination, in the options, in all the options, if you find pi, then naturally we have to bring the answer in terms of pi. So at that time, you should not put the value of pi, you should leave pi as it is. Okay, fine. Read now statement of sum number 3. Come on, read it. Look, what is the situation here? We have one extremely long, thin, straight wire through which current is passed. Fine. And then you can expect, current is a source of magnetic field. Because current is passing, it will produce its own magnetic field. At distance y from wire, at perpendicular distance y from extremely long, thin, straight current carrying wire, you know the magnetic field formula from third semester, B equals to mu 0 I upon 2 pi y. Mu 0 I upon 2 pi y, where y is perpendicular distance. Right now perpendicular distance I am taking r. So instead of y I have placed here r. But why the sign is there for cross? Cross means inside magnetic field. Why magnetic field is inside? Look, if you want to find out direction of magnetic field at this point, then what you should do? You should hold this current carrying straight wire in your right hand palm such that thumb should be pointed in the direction of current, and then in whichever manner the fingers of right hand palm take the turn, in the same manner magnetic field lines also take the turn. So magnetic field lines whirl around this wire this way. This way means from here they go inside. That's why I am putting small symbols of cross. It indicates magnetic field perpendicularly inside the plane of the figure. Fine. Now we are given here one very small ring having radius a, which is coming from very far distance. It is moving with constant velocity v towards this wire. And during the motion, when that ring comes at distance r, at that time we are asked to find out induced EMF in this ring. How to find out? I am showing you. Induced EMF according to Faraday's law, minus d phi by dt. So minus d by dt of phi. Again, here area of this ring is perpendicular to the uniform magnetic field. Sorry, not uniform, only magnetic field. Here cross section is perpendicular to magnetic field. Whenever cross section or area is perpendicular to magnetic field, you should use the formula phi equals to AB. Phi equals to AB. Fine. Phi is equal to AB. Now tell me minus d by dt as it is. What about A? A is the area of this ring. Because it has radius small a, I should write area as pi into a square. Pi into radius square, radius is a. And what about value of B? Actually this is the value of B at distance r. But this ring is very small. You are given in the statement that A is very much smaller than r. Because this radius is very small, you can say almost same intensity of magnetic field you will have at all the points on the cross section of this ring. And because of that, we treat the value of B nearly constant equal to this much. Mu 0 I upon 2 pi r. Mu 0 I upon 2 pi r. Fine. Mind well, this value of B is true only for very small ring. It should be very small in comparison with, radius of the ring should be very small compared to this perpendicular distance from the wire. And you are given in the statement A is very much smaller than r. Fine. Now tell me, pi and pi will cancel. Then minus mu 0 I a square upon 2 into d by dt of 1 upon r. Can you take derivative of this part directly with respect to time? No. Inside is the part of, inside part is a function of r. Then we should take derivative first of all with respect to r, and then separately we should take derivative of r with respect to time. Fine. Apply chain rule. This part as it is. This part as it is. And now instead of d by dt, what I have written here? D by dr. And 1 upon r as it is. But now I should differentiate r with respect to t. Again, apply chain rule here. D by dr of 1 upon r into dr by dt. Fine. Now this minus mu 0 I square upon 2 as it is. Come on, 1 upon r, its derivative with respect to r, it is minus 1 upon r square. How? If you take this r up, it will be r raised to minus 1. Then you know d by dr of r raised to n. What is it? N into r raised to n minus 1. Similarly here, minus 1 into r raised to minus 1 minus 1. That is minus 1 into r raised to minus 2. Bring it down in the denominator. So you will get minus 1 upon r square. That's why I am putting here minus 1 upon r square. And what is this dr by dt? It is time rate of change of position of a body. Come on, time rate of change of position of a body is going to give you instantaneous velocity. Here velocity of this ring is constant equal to v. So this can be replaced by velocity of ring, let it be v. So now minus minus plus mu 0 I s square v upon 2 r square. I repeat, minus minus plus mu 0 I s square into v upon 2 r square. Tell me, here as time passes on, what will happen? As time passes on, what will happen? Because this ring is coming closer and closer, closer and closer, then distance r will decrease. As r will decrease, come on, induced EMF will keep on increasing. Okay.